Okay, then let's continue. So we've made one step towards Basels, and now we're making the second step, which is actually a little bit bigger in terms that we're getting closer to it, not necessarily more complex. I don't know. Intrinsic volumes. That's now the next big topic. Intrinsic volumes. And intrinsic volumes have a number of names. They are sometimes also called Quermaßintegrale or Dehn-Steiner functionals or integral curvatures. One other term you find in the brain imaging literature, specifically by Tom Nichols, is the term Minkowski functional. So if you read Tom Nichols' work on data analysis in neuroimaging, you might come across this term, Minkowski functional. And these days, actually, so as of 2017, in the SPM literature, also since like 2010 or so, with 2017 I meant the recent Adler works on this, and in like from 2010 to 2015 or so, also in the SPM world. So, for example, if you look into what Guillaume Flandin, I guess you pronounce him, and Carl Friston have written in recent years on topological inference, they use the term Lipschitz killing curvatures. But the thing is that these intrinsic volumes are a specific form of Lipschitz killing curvatures. There's also a paper by Gareth Barnes that uses these LKC notion for EG and MEG inference. So these are all just words and terms, or names better, which don't explain anything so far. It's just fancy names. So the whole thing about intrinsic volumes came really into the neuroimaging world with the paper by Worsley, 1996. In human brain mapping, where results and intrinsic volumes were introduced, and the nomenclature in that paper is actually only on results, and I tried to separate them a little bit out because intrinsic volumes and results are still different things. Intrinsic volume is something that you can have even without a random field and without smoothness adjustment. Result is something that combines smoothness adjustments and intrinsic volumes. And Worsley, in this paper at least, uses both concepts a little bit intermingled. But then I think later the consensus is really also in the work of Jonathan Taylor in the since the mid-90s, and then up to basically this day, it becomes clearer that there are intrinsic volumes and that there are results. The problem with intrinsic volumes is that to really introduce them from first principles is even more impossible, essentially, than for the back measure, because intrinsic volumes, they are deeply rooted in differential geometry and integral geometry, which are all mathematical fields. So we would have to make a long detour through differential geometry and integral geometry, which of course we cannot afford to do, because we have to publish papers to make sure that we can pay the rent and buy food for our cats, at least for my cats, and food for me. So we cannot go through this fascinating field, but we have to start somewhere. And I'm starting with a definition that is implicit, and you will see what I mean by implicit in a second. And I'm following with this whole section on intrinsic volumes. I'm actually following what Jonathan Taylor has written in one of the books. So we are now getting more into this whole business of geometry versus random processes, and that's kind of special. And there are recent books by Jonathan Taylor and Adler. So there's a book from 2006, I believe, which is quite mathematically advanced. But there's also a book that they started to write with Keith Worsley that is a little bit more on the applied side, so which is a little bit more easier to access from a new imaging viewpoint. However, this book is so far unfinished. You find that on Robert Adler's website, where you also see the countdown until when he will retire. So he's somehow looking forward to his retirement. Anyway, so I'm following quite closely how Jonathan Taylor introduces intrinsic volumes without an excursus to differential integral geometry. Yeah, things will again get simpler once we went through the general definition. But I wanted to. So the problem is always, if you know what an intrinsic volume of a certain, what the intrinsic volumes of a certain geometric shape is, that's fine. This is what we will also see in a second. But then you still don't know what an intrinsic volume is. And I always find this a little bit weird. So I like definitions. And when you say an intrinsic volume is that and that and that, then I feel like, okay, now I know what an intrinsic volume is. And then I can say, okay, the intrinsic volume of this and this and this is that and that and that. Good. However, this definition can only be implicit, and it works like follows. Intrinsic volume definition. Let S be a subset of RD. So that's again our search space for which we now want to define a notion of intrinsic volume, whatever that should mean, but that's what we're trying to define. And let a tube TSR of radius R around S be defined as follows. So you also find there's one review by Robert Adler which is called whatever and tube formulas. So tube formulas, this is where this is coming from, because the intrinsic volumes can be defined in terms of these formulas for tubes. So what are tubes? Tubes are something relatively intuitive, defined as follows. So a tube TSR, so first of all, a tube is always defined with respect to some other geometric object or some other set S. So you cannot have a tube without a reference object. They are defined as follows. A tube is the subset of elements of the d-dimensional space which have a distance to the object that is smaller than the radius. And then the question is, what is this distance formula, or distance metric, not formula, what's this distance expression? That is, in this case, defined as follows. For a tube, it's the inf, so the minimum, for all that matters here, it's the minimum over all possible points in oops, that's also, oh, that's right, sorry. Over all possible points in y. Yeah, so again, so the distance between the point x and the tube, the distance between the point x and the set S is defined as follows. It's the minimal distance that a point x can take for all points y that are in S. That's something one needs to think about a little bit, but one gets to a certain intuition, and I will show you that with a triangle and with all my power of imagination, whatever that should mean. So we will discuss this tube around this triangle in a second. Now, the idea is the distance from a point X in R2, so R2 is here our space in which this triangle lies. The distance of a point X that is within the tube around this triangle, so our triangle is called S, the distance should be smaller than R, and the distance is measured as the minimum distance from any point in Y. Yeah? So the way I visualize that is as follows. If you think about the triangle, maybe now actually lying on your table in terms of a metal thing, and you take a line of chord, something like this, of length R. Yeah? So you're going, you have a length, this is your length R, and this is where you, so it's basically around here, and you can move it. It's a line of chord, yeah. So you can also, for example, it's a line of chord, and Faden, yeah. And you can also move it around, so you can also have it here, so like you would have when you move it. So then you should go to a distance R, but you should at the same time be at the minimum Euclidean distance from any point in R. So you, in S. So you should go as far out as possible, essentially, which and as possible means R, as possible with your this thing. That's easiest. So this is fixed here to the triangle, and you should go as R out. So you should have a distance R. And you should take the minimum over all points in S. So the way you can visualize that is that if you have that a little bit tilted, then it's not the best explanation. Let's first do what happens actually at the corners. So that's where I can do it better. So at the corners, you come out with going rectangularly from the triangle, and then you need to keep the distance R, but also be at the smallest distance from any point in Y, and that's easiest at the corners because the smallest distance from any point in Y, the point in Y that matters is exactly the corner. So you need to stay as close as you can at the as close as you can from the triangle, but at a distance R. Yeah? Which then induces that you actually have to go around this arc on this chord. So that's and this happens at all of these things at the triangle. What I'm having some problems to express in words right now is why you have to actually go in this rectangular manner. Let me think again about my rectangular manner. When you are at the side of one of these triangles, you have to have a distance R and the minimum of all points in S smaller than R, maximally R. I had it. I always, when I'm actually using the tube, I always think about this problem why is the rectangular the right way? I can't explain it now. I have to think again. Maybe it will come to my mind, and then I will say that. Does anybody have an idea why it has to be rectangularly from this definition? No, that's fine, because I also can't explain it right now. But it has to be rectangular. So you actually, if you define the tube, you actually define this. Yeah. So the original triangle was the triangle S here, and now we have defined a tube by basically respecting this distance function. and including all points x which are at a distance that is smaller or equal to r from the set S. Yeah? So the tube, the two-dimensional tube is what I'm now indicating here. Of course, you can also, and that's interesting, you can also have a three-dimensional tube around a two-dimensional object, and I think that's quite easy to visualize. So in my mind, I can. So it's basically something like this. If you think that there's a rectangle in there, so there's a rectangle in there, and this is of course a two-dimensional entity. It doesn't have a 3D extension or a 3D Ausdehnung. Now if you again use this idea that you have a little cord, what's the Faden? I don't come up with the right thread, a small thread that you move around here and always keep at the same distance, but also at the minimum distance from any point in the in the set, then you get something like this. Yeah, and that's a tube. And the question is now, and this is where the intrinsic volumes come in, is what is the Lebesgue measure of a tube? That's why we talked about a Lebesgue measure. Now the Lebesgue measure of a tube, which is defined as I did there, and try to, at least for the corners of the triangle, get clear, not quite for the sides of the triangle. The Lebesgue measure of a tube is, and that's a result from integral geometry, is given by the sum over, no, that's fine, b d minus I. So these are, we will see that in a second, the volumes of the balls in R. So these Bj, they are the Lebesgue measures of balls in J dimensions. So this is something that we've just seen. This goes from J d minus, also d minus I, E from 0 to 1d. So these are these balls. Again, we are talking about the Lebesgue measure of the tube, which is given by a sum. It includes the balls, the volume of the balls in these dimensions. It includes the radius of the tube, so that's the radius of the tube to a certain power, and that's the important thing, it includes these terms here. These, let's do that in red. These coefficients. And these coefficients, this mu d, they are the intrinsic volumes. And this is why this definition is implicit, because it doesn't really imply, doesn't really define the intrinsic volume. It just says you need the intrinsic volume to compute the Lebesgue measure of a tube. Which at first means that you have to understand what a tube is, that you have to understand what the Lebesgue measure is, and then you are still left with the fact that the intrinsic volumes are actually coefficients that you need. So again, this is not something that really allows you straightforwardly to compute intrinsic volumes. However, and this is now follows quite closely to what Jonathan Taylor does, if you think about this formula, and I will not do that now because it's rather the chances are high that I confuse myself and at the same time you. If you think about this formula and apply it to the tube around a triangle, then it becomes a little bit more intuitive. So think about this tube, or this two-dimensional tube around the triangle, and now take my word that if you write out this formula that I gave you in all generality a second ago, if you write that out, you get the following special case of this formula. You get p r squared times mu 0s. So the first, the zero order intrinsic value, you get 2r mu 1. So this actually, so what this, where this pr square, this comes from the ball, right? We talked about the Lebesgue measure of the ball previously. Finally you get mu 2s. And now this is, what this describes is the volume of the tube around the triangle, where actually the tube comprises also the triangle itself. So, so this is again our tube here around, but if you compute the volume of the tube, so the tube is really defined, as we've seen before, as all the x that have a smaller distance than the radius, which also includes s, of course, but I try to differentiate here the object that it starts from this construction of the tube around it. Now, again, if you apply this formula that I written just up and basically use the special cases that apply in a two-dimensional case, then you end up with this formula, p r squared times mu 0, 2r times mu 1, and mu 2. That looks a little bit weird. Because I was doing something else in my mind there. Mu 2s. And now from this, one can roughly infer what these coefficients must be, because we are interested in the intrinsic volume. So we have to somehow figure out what is this, and what is this. And now it tells, the formula tells us that the volume or the area of this geometric thing that we just constructed as the tube around a triangle says that, well, the volume or the area of this thing is given by this formula. Now, if we think about it, let's do that. So first of all, this thing here, pr squared, this looks a lot like the area of a disk, as we discussed previously. And now if you use a little bit of geometric intuition, if you look at these things here at the corners, if I think it's a little bit nicer in the script, you can, with intuition, think, okay, they make up three parts of a circle. Yeah, I think that's, if you look at the thing in the script, that's a lot easier to see if you think about the gray things and you put them together. So you use the gray things at the corners of the triangle and you just put them together, then it's fairly intuitive to see that this is a circle. Of course, you could now go and try to prove that based on what you know, how much the angles in a triangle and how they propagate if you have a 90-degree angle there and so on, but yeah, intuition, this is a circle, which implies, if we are computing the area of this whole thing, that this one must be 1. So this essentially means that mu 0 of this, so mu 0, so the zero order intrinsic volume is 1. It will turn out that actually the zero order intrinsic volume is the Euler characteristic of the set S. And we will have to talk at some length about Euler characteristic. But the Euler characteristic is for the things that we are mainly interested in, it's always 0 or 1. And in this case, it's 1. Now the second intrinsic volume works as follows. If you now think about, let's use yellow maybe. If you think about these things here, and computing their area. Then, of course, these are rectangles, and they have certain sidelines. So one is, of course, R, we know that. And then they are, of course, built by the side length of the triangle. So if we call the triangle side lengths here A, B, and C, and we compute A plus B plus C, which you also call the perimeter of this times R, then we get actually this yellow contribution. Now, this yellow contribution is supposed to be taken by taking twice, so we can account for this by actually just using 1/2. So the mu1 then for 2D objects comes out as 0.5 the circumference. I think that's another word for perimeter, might be something different. Circumference, which is A plus B plus C in this case, of S. This is what I explained, and you can already write down Euler characteristic, although we don't know at all what that means, but we will have to talk about it in some length. But then not that much length, because we will only approximate it, the beauty of p-value correction. So that's the Euler characteristic. That's a half of the circumference of S. And finally, this last bit must be then the thing in the middle, so the triangle itself, so this thing. And this is, from what we learned this morning, just the area of S, or the Lebesgue measure, or whatever you want to call it. So that's the area of S. Yeah. So from this hand wavy, there's a tube, and then we look at the Lebesgue measure of the tube, and then there are these intrinsic volume coefficients. One can at least motivate, let's say like that. One cannot really understand it in a logical fashion, but one can at least motivate that mu0 is the Euler characteristic, mu1 is the 1/2 times the circumference, and mu2 is the area of that. If we have a set, and this is actually what we're more interested in, if we have a set that is a subset of R3, then it remains roughly the same, but only quite, because then we have, also according to the, I think it's called Steiner formula, Den Steiner formula, the formula that I showed you above, then you have one more intrinsic volume, but the zero order intrinsic volume remains the Euler characteristic. The mu1s I will talk about in a second. The mu2s is 0.5 the surface area, which is fairly close to what we've just seen there, but not quite, because we're now in 3D. So our S is now 3D. The surface area, the mu3 is the volume, used to be the area, and the mu1 is twice the caliper diameter. Now the caliper diameter, one can, of course all of this is of S, so we want to have the intrinsic volumes of S. Now the caliper diameter is again something that one cannot easily compute, so you need a caliper, which I didn't know what it is, so I took a picture of it from the internet. So you see what a caliper is in D. So it basically allows you to put objects between two planes, something like this. And then the caliper diameter is the average? I guess the average is in the average, yeah. So it's the average over all rotations of the object. And of course, you cannot easily, so you would have to rotate it. It's something that people in the geosciences to measure rocks and so on. That's something where this plays a role. Now, these are the general things. If you look into the Worsley paper and also now into my handout, again, things simplify to some degree, although you don't really know what these are, if you look at the intrinsic volumes of familiar objects. So if you, that's now in the table, if you look at the intrinsic volumes, let's just do the rectangular ones. If you look at the intrinsic volumes of a line, of a rectangle, and of a cuboid, then from this general definitions that I brought up there, oops, so, are we recording? One can now ask, so what are the intrinsic volumes of these familiar objects? Ah, Jesus, what is going on? It's not really optimal, this. Hello. Got something funky. Maybe it's the sweat. So I'm sweating and it's getting wet. So we have these familiar geometric objects, a line, rectangle, and a cuboid. And the question is, what are their intrinsic volumes? Now we learned in 3D, we learned that the highest, let's not start with the highest order. Let's look at them and then talk about them. So this is a line of length A. This has a zero-order intrinsic volume of 1, which is its Euler characteristic, and it has a first-order intrinsic volume of A. It doesn't have a second, or the second and the third-order intrinsic volumes are zeros. The rectangle, which has a width A and a height B, has again a zero-order intrinsic volume of 1, which is just its Euler characteristic. It has a first-order intrinsic volume, and that's now interesting because it's something a little bit different from your general notion of volume, but something that, yeah, of course, one can quantify. A plus B, so that's the 1/2. Essentially, it's circumference. So A plus B is its first-order intrinsic volume, and then its second-order intrinsic volume is A times B. And its third-order intrinsic volume is 0. Now, the cuboid of width A, height B, and depth C has again a zero-order intrinsic volume of 1. It has a first-order intrinsic volume of A plus B plus C. This is the caliper thing. It has a second-order intrinsic volume of A times B. So where it does basically all combinations, A times C plus B times C. And it has a third order intrinsic volume, which is again just its volume of A, B, and C. And of course for fMRI, we are primarily interested in this. And these things are actually, if we later look how the whole framework of p-value corrections apply to fMRI, these things are actually computed for the voxels of the brain. Of course, you have more than one cuboid there. So there's this algorithm, which you also find in the Worsley paper from 1996, which is implemented in this C function, as I mentioned last time, which is called, I think, SPM Riesel volumes or so on. This implements an algorithm to compute for an arbitrary collection of such cuboids, which are called then a picture of the brain, computes these intrinsic volumes. Yeah, Good. So intrinsic volumes, kind of a tricky thing to introduce, because one way is to do a course in differential geometry and then have a language to talk what intrinsic volumes are. The other thing is not talking about what intrinsic volumes are and just telling the world that the intrinsic volumes of familiar geometric objects, and you find disks and hemispheres and spheres also there, are these. It's also fine. I mean, one gets somehow a feeling already from just looking at this that this is somehow sensible, but one doesn't have kind of one, after this, one cannot really say what the intrinsic volume is in general. What I tried to say is a little bit more about what the intrinsic volume is in general, but then it's an implicit definition, which is also not that great, but at least it's a definition as coefficients in the formula for the Lebesgue volume, this or Lebesgue measure, for these tube constructions around geometric objects. Lovely. And you do all of this when you click results show in SPM. So never, and FSA and everywhere. Good. One last thing. No, there are two last things actually, because we have to still talk about the results. To now define results based on intrinsic volume, we have to make one further assumption. But first, are there questions about intrinsic volumes that don't concern the formal thing, but the intuitive thing? Any questions that I might be able or not be able to answer?
How did Worsley realize that you may try to do the problems of these edge or boundary?
Okay, yeah, so the way I introduce it there is that if you want to figure out the probabilistic properties of excursion sets, and you say, okay, it depends on the volume, for example, where we haven't really talked about this whole thing, but this is a little bit why that might be a little bit hard to explain. Because what they were really after is a formula for the probability of the maximum of a random field to exceed a certain threshold. And this is why they built this whole thing. But then this is not the only thing that is necessary for this whole cluster business, so this is why I haven't introduced that yet. Anyway, if you think about it, that this depends on the volume, then you can also, if you visualize a random field, so that's how I visualize it, if you visualize a random field, in multiple dimensions, then you get the feeling that if you only account, for example, for the stuff that is, that's the way I visualize it, that if you only account for how often you have this kind of volume and never really look at what's happening at the edge. So if you're basically looking only at the intrinsic thing and you're not looking at these edges, then you might miss something. That's how I visualize it. But really, you can. Really, I think it was just in the. It's just in the expression for that that Adler derived for the approximation of the Euler characteristic, where these things were in there, and then in the first attempt that Carl Friston did, they only looked at one-dimensional things. In the second one that Worsley did, they only looked at two-dimensional things, and then it was time to look at three-dimensional things because the brain is three-dimensional. And then they had to put everything in. A lot of this will, this on the history will become clearer if we actually look in more detail while we are talking about all these fairly basic things. But if I hadn't introduced these fairly basic things, then it makes no sense at all to understand how these formulas for example, the cluster size or whatever, where they come from. So you need still some patience and trust that I'm not leading you astray, but I showed you in the SPM table that there's Riesel, so if you believe the SPM table, then you cannot believe me. Okay, I want to go on now. We have answered one question because I want to really finish with Riesels today. So one thing that goes into the Riesel computation is if you have a three-dimensional object, then the first intrinsic volume, at least this is how it's computed in SPM, needs to be decomposable in, needs to be decomposable into, maybe I just write here, into contributions from all the three axes. So basically the first order intrinsic volume needs to be decomposable into contributions from the x1, the x2, and the x3 axis. And the second order intrinsic volume needs to be decomposable into contributions from all combinations. If you look at the formulas that we just saw for the rectangles, you actually see that. So if you look at the three-dimensional cuboid, you see that there are these contributions. Because there's this, I will show you that in a second, there is this a plus b plus c, which is a contribution from the x1, the x2, and the x3 axis in 3D. And for the second intrinsic volume, there's the ab, which is the x1 and x2 contribution, the ac, which is the x1 and the x3 contribution, and the bc, which is the x2 and x3 contribution. Why is this necessary? Because it's necessary to define results. And now the high point of today's class, definition of Riesel volume. And that's actually simple compared to the rest. Now we are actually, so far we've just talked about geometry, right? So we talked about subsets of real d-dimensional space, but there were no random fields involved anymore. Suddenly the random fields disappeared. Now the random fields come back, and we assume a random field x, so big X, over 3 dimensions. So we are only interested in domains of random fields that extend over 3D space, because we're interested in brain images after all. And we assume that the smoothness of the random field is expressed in terms of this reparametrization of our smoothness measure that we discussed last week on video, or in the basement with Rasmus and Lilla. And this involved these full measures of full width half maxima, which were these imaginary things of this white noise convolution. I really didn't come up with this, right? I did not come up with this. I'm just trying to say what's going on. Anyway, so these are these imaginary convolution kernels from this white noise that generates the same smoothness as our current field. And then let S be a subset of the domain of this field, so the 3-dimensional domain. And then the Riesel volumes of S. So the Riesel volumes of S are defined as follows. The zero-order Riesel volume of S is the zero-order intrinsic volume of S. That's the Euler characteristic, and we will see that. Now, the first order Riesel volume of S is essentially the smoothness adjusted intrinsic volume of first order of S. So it's as simple as multiplying this smoothness parameter with its intrinsic volume contribution, and doing this for all of them. So you see that now the Riesel volume depends both on the intrinsic volume, which is a geometric property, and the smoothness, which is a property of the random field that extends over this space. And the Riesel volume increases with smoothness. So if you make fx larger, so you make this hypothetical Gaussian convolution kernel broader, so you increase the smoothness of the random field, then you get a larger Riesel volume. But if you also make the intrinsic volume, so if you just make the thing bigger, so the S bigger, then you also increase the Riesel volume. Let's finish this. So you multiply the intrinsic volumes with this smoothness. The R2 is basically then follows the same logic as for the intrinsic volumes. So you need these contributions in these pairs of dimensions. Plus so that's the contribution of the intrinsic volume in the x1 and x2 dimension. If you look into the Worsley paper from 1996, there's this algorithm section. This is essentially where this is coming from. We will go over this algorithm, but here we have now established its foundation. As I said, you find it in the SPM toolbox. In this SPM Riesel volume, x1, x3. So these are these pairwise contributions, and finally the volume that matters actually most. The third order Riesel volume is just the product of these convolution width in the 3 dimension times the third order intrinsic volume, which is just the Lebesgue measure of the volume of the thing under consideration. So why was this week so horrible? The course, it was so horrible because the results are defined in terms of the smoothness measure, which was relatively okayish, although this reparametrization is not the nicest thing ever, but at least it's something and one can grasp. It was so horrible because the results are defined in terms of intrinsic volumes. And intrinsic volumes are defined in terms of Lebesgue measure. So to start somewhere, we had to start at Lebesgue measure, went over intrinsic volumes, have the problem that these are things that are quite deep in their respective mathematical disciplines. I had to just look superficially what they are, but hopefully with especially these formulas in the table have kind of an intuition of what that means. And it's all not a joke. This is actually all computed in SPM every time you compute the p values. So it's also not completely like I'm doing theory stuff that is not of important for anything. It's important for every fucking fMRI result that is reported in the literature with a p value that is family-wise error corrected. Good. These are the Riesel volumes. We will come back to them. We will actually need them all the time now because they are found in all these formulas for the probabilities of things of excursion sets. But I think we have now actually have the kind of foundations actually behind us, because we have now talked about random fields and we talked about geometry, and now we can use this knowledge like the veterans and heroes of cognitive neuroimaging, so Pete Worsley and Carl Friston, can use this knowledge to actually apply that in the context of thinking about what's the probability of seeing a cluster or a maximum of a certain height, a cluster of a certain size, under the null hypothesis that the random field has a mean expectation of 0 and a given smoothness. And this is what we will start from next week. Yeah? Any questions? No. Good. With respect to the study questions, you see they are really about the intuitive thing, and this whole lecture is really about, at least if somebody says the next time results are the independent tests that you compute, then you would say, well, are they really? So I learned something completely different about them, and you learned the right thing. So at least you are then confused when somebody says that, and you can start a debate, and you will turn out to be right, and this other person will turn out to be wrong. Good. Then let's meet in a couple of minutes, 5 past or so, in the other room for the other course. Good night.